Okay, so we're going to prove that if A complement is the complement of A, right? So if A to the C is the complement of A, then the probability of A complement is 1 minus the probability of A. And we're primarily going to be using axiom 3 and axiom 2. Okay, so let me scoot it down a little bit. Axiom 2. All right. So, proof we know that. So we know that A union A complement is equal to S, right? Remember we have our sample space. Oh, our sample space is S. And let's say this blob here is A. That means everything outside of A that's in S is A complement, right? So A union A complement is the entire sample space, right? And we also know that A and A complement are mutually exclusive, right? By definition, A complement is all the elements in S and not in A, right? So, and we know that A intersection A complement is equal to the empty set. So now we can use axiom 3. So let's go ahead and do this first. So A union A complement is equal to S. This implies that the probability of A union A complement is equal to the probability of S. And then by axiom 3, so let me do by axiom 3, I know that the probability of A plus the probability of A complement is equal to the probability of S, right? Since I know that A and A complement are mutually exclusive, I know the probability of their union is just the probability of that set plus the probability of that set using axiom 3, right? Now I'm going to use axiom 2. I know that the probability of the sample space is 1. So by axiom 2, I know that the probability of A plus the probability of A complement is equal to 1. Now I want to get the probability of A complement is equal to 1 minus the probability of A. Well, all I got to do here is subtract probability of A from both sides, and then I'm done. So subtracting probability of A from both sides, I get probability of A complement is equal to 1 minus the probability of A. And that is our proof.